Good afternoon, everyone, and thanks for having me. Today, I am excited to share the story of our very first customer delivery utilizing quantum computers at SAS. In this project, we explored how classical and quantum optimization solvers can be used together to solve a complex real-world problem from the consumer packaged goods space. A quick intro, I'm Sertalp Cay, lead quantum optimization developer at SAS, and I'm also part of the delivery team behind this project. I have been with SAS for 11 years, and I have been part of our quantum program since its inception nearly 3 years ago. And even outside of work, I am a bit of an optimization nerd. I co-host a podcast on applying optimization techniques to fantasy sports, specifically Fantasy Premier League game. And this past year, actually, we took home the Bronze Award at the Football Content Awards in London. And I'm hopeful that our work into quantum optimization will give us an extra edge and help us stay ahead of the competition next season. And here's a quick roadmap of what I will be covering today. First, I will set the context by introducing the key players involved in this project. Then, I will walk you through the business problem and explain why quantum was a compelling part of the solution. After that, we will dive into our solution approach. I will talk about both classical and quantum and look at the results. And finally, I will wrap up with the impact and the key learnings we took away from this engagement. So let's start by setting the stage, who was involved and why this project came to life in the first place. Starting with SAS, in today's world, being data-driven is not enough. You need to be outcome-driven. That means using analytics and AI not just to analyze, but to scale human productivity and decision-making. And that's exactly what SAS has been doing for nearly 5 decades. We help our customers extract insight from data and turn it into action. Today, we continue this mission as a data and AI company. We deliver fast, productive, and trustworthy solutions. We are leaders in areas such as artificial intelligence, data science, predictive analytics, and decisioning. And we work across industries that are especially ready for quantum transformation, including life sciences, manufacturing, banking, and capital markets. Now that you know a bit more about SAS, let me introduce the other key players in this collaboration. Many of the world's most innovative companies are SAS customers. Actually, 90 of the Fortune 100 companies are SAS customers, and the customer in this project is actually one of them. A multinational Fortune 100 company coming from consumer packaged goods sector. We have partnered with them for over 45 years, and we delivered several groundbreaking projects during this collaboration. So when it came time to choose a partner for our first quantum delivery, so they were the natural choice. So we have analytics. We have a customer ready to explore this space. So what's missing? The quantum piece. Knowing that our customer was interested in solving a real-world optimization use case made D-Wave the perfect fit to address their problem. With all 3 pieces in place, it was time to find out what's possible and what we can do with this problem. So now that we have set the stage, let's dive into the core of the engagement, the what and the why. So let me start with explaining you the challenge our customer was facing. So they manufacture a large number of liquids on relatively few production lines. So they have very complex rules about which products can use which equipment, which streams can go into which products. So in this case, the goal is to find the optimal assignment of streams into tanks and tanks into products, while respecting all kinds of different constraints. For example, making sure certain products never share the same equipment, certain streams never make their way into certain products. This sounds very straightforward. It's an easy problem to understand, easy problem to state, but the scale and complexity of this problem snowballs really fast. To give you a sense of the scale, with up to 250 products and just 6 tanks, the number of possible combinations in this problem is astronomical. It is approaching 10 to the power 114. Now, to be clear, the number of combinations isn't always a good indicator of how hard a problem is. But it does tell you one thing, that you can't just throw any brute force method at it. You need something smart. So for these kind of problems, we usually use mixed integer programming, and we try to solve these problems to optimality. So the good thing about our solver is it always finds the best solution, but as the size grows, it demands much more time and computing power. So that's what led us to explore quantum as a way to help to reduce that time without sacrificing the solution quality. So we know the problem is complex, but what's the value of solving this problem better for the customer? So first, the current approach the customer is using is very expensive and time-consuming, and no production line wants that. And second, this is just one production line in one facility, and if we can crack the code here, you can scale it across the organization. And a single run here involves hundreds of tons of liquid per day. So even a small percentage improvement here leads to major cost savings, and more importantly, waste reduction, and that ties directly into our customers' sustainability goals. On top of that, this is an optimization problem with a wide feasible region, which I will explain in a minute. So it's a very sweet spot for quantum technology. And finally, this project gave us a way to actually move beyond the quantum is 5 years away narrative by making something happen now on an actual customer problem. So I mentioned this problem is a good fit for quantum, but what makes it so? So first, core of the business problem is about assignments. So decisions that map cleanly to binary variables. And for quantum solvers like D-Waves, so they are built to handle binary optimization problems directly. In this case, there are no continuous variables, no integer variables, just pure binary logic, so it's a pretty suitable problem. And second, there's a nonlinear relationship between streams and products when we are trying to measure how much stream we can use in the final product. So they have to calculate this and determine the amount based on this formula. So this logic can be modeled as a quadratic expression. And quantum solvers are capable of dealing with quantum expressions. You can even move this relation into the objective function of the problem and solve very efficiently. And third, and most importantly perhaps, the size grows really fast. So the solution time grows really fast. Problem own size also grows really fast. Classic solvers can handle small sizes of these problems very easily. But when we get closer to the real world sizes in terms of number of products, tanks, and streams, then the solution time gets excessively long. So just to summarize, it's a meaningful problem for the customer. It's a technically challenging problem at the same time. So it was perfectly suited for a hybrid quantum classical approach in our minds. So writing this problem in SAS's classical optimization engine was pretty straightforward. So we have lots of experience in translating these kind of problems. And any optimization problem has three main parts. The objective function, what you are trying to maximize or minimize, so that's your target. Variables, what you can control. And finally, constraints, your limitations. The objective here is to maximize the total stream used in products. Or in other words, we are trying to minimize the leftover in tanks. In terms of variables, we had two main sets of variables. Since this is an assignment problem, we are assigning streams into tanks, and we are assigning tanks to products. But on top of these two sets of variables, we have two more sets of variables, what we call auxiliary variables. So they are added just to linearize that nonlinear measure I have just mentioned. So the first of these auxiliary variables keep the relation between stream, tank, and product. So we are checking which stream used which tank and in which product. And the second one is just checking which streams are inside which products when we solve. So these two sets of variables, the last two, increases the problem size and solution time very significantly. And constraints are relatively simple. So the first constraint we have is making sure that every stream go to a single tank only, and exactly one tank. Each product draw liquid from exactly one tank only. And we have some input and output balance for each tank. And finally, we have some constraints to linearize that relationship between streams and products. So now we have reviewed the problem and the potential impact. Let's take a look at how we approach the solution using quantum optimization and whether we were able to deliver. So throughout this project, we experimented with multiple formulations and solvers from D-Wave. So 3 formulations across 2 solvers to be exact. And our first attempt was to use a CQM solver, constrained quadratic model. The reason is because the formulation on how you write the CQM is very close to how we model the classical algorithm, classical model. So you can almost directly translate into CQM and send it to the D-Wave's solvers. But we quickly ran into some scaling problems. Because of the linearized logic, number of variables and constraints in this problem grows so large that even though we were able to solve smaller sizes very effectively, when we came to the real-world sizes, we actually hit the constraint limit. Then, D-Wave's technical team, and a huge shout to them, they introduced us to their nonlinear solver. And that was a game changer because with this, we could express that nonlinear logic I just mentioned directly inside the model without a need to linearize it. That meant the number of variables dropped from 159,000 to only 1,600, and number of constraints dropped from 473,000 to only 300. And even better, when we are calling the solver, we were able to get 7 feasible solutions every time we call their solver, and nonlinear solver returns 32 solutions in each call, and we were getting 7 in average, which is pretty decent. But later, again, with the help of the technical team, instead of using encoded variables, binary variables, we learned that we can also use categorical variables. So they are actually integer variables, but they said, with nonlinear solver, this is not a problem, you can use it. And when we actually switched from binary to categorical variables, the problem got even smaller. Number of variables dropped from 1,600 to only 300 now, and number of constraints is just 5, and that's the tank input-output balance. Like, you can't get rid of those. And the great thing is, now we are getting, in average, 30 feasible solutions every time we call the solver. So that's a pretty good number because we get only 32 in every call anyway. So 30 feasible solutions means that actually the problem is pretty suitable to use quantum. And not only we got more feasible solutions, the solution quality was better too. So with this compact formulation that we ended up using with D-Wave's nonlinear solver, we were able to get solutions in just 2 minutes. So this is where quantum solvers really shine, in our opinion. The speed is unmatched. But on top of that, there is something that's discussed in the morning sessions, is that you also get multiple solutions. You get a variety of solutions across the feasible space. Actually, this is not something you get from classical solvers. So when you use classical solvers, you get only the optimal solution, and that's not enough to draw some insights about the problem. But when you get a variety of high-quality solutions, then you can actually have a look and see, what's common between good solutions. What are the variables, what are their values, and then you can come up with a smarter approach. But as I mentioned, we always use classical solvers when you need the optimal solution with a proof. And in mathematical optimization, proving a solution is optimal is actually a very hard problem. Even if I give you the optimal solution alongside with the problem, you need to prove that it's optimal, and that's a challenging problem as well. But classical solvers excel at this. So they provide you a proof of optimality. However, so the trade-off is obviously the speed. So when we give this problem to our classical solver, we are getting obviously the proof of optimality, but it takes 6 hours to solve this sample problem. So then we asked, why not combine the best of both worlds? Like, obviously, hybrid approach is something we talked a lot. And in this case, we did something very simple. We call quantum solver first, and we get a variety of high-quality solutions. We process them, and we generate one final solution to feed into our classical solver. So this is what we call our hybrid method. And when you have this quantum and classical hybrid for this problem specifically, you get proof of optimality, you get feasibility detection, you get everything. And more importantly, the speed is just 12 minutes. So in just 12 minutes, we are getting a proven optimal solution for this problem. And that's actually what we were looking for in this engagement, because we wanted to be able to use quantum and classical computers without sacrificing either the speed or the solution optimality. And as a final experiment, we wanted to understand how to best use our allocated quantum solver time. So in classical optimization, the longer you run the algorithm, it's better. You either get an improved solution or you get the proof of optimality at the end. But quantum behaves a little differently. Even though running it longer gives you better solutions in average, in our opinion, the real strength of quantum solvers are coming from running them more often and getting a variety of solutions. So in our tests, we found that shorter, more frequent calls give us consistently better solutions compared to fewer, longer ones. So specifically, we saw better solutions by calling the quantum solver, let's say, 4 times for 5 minutes each, as opposed to running it only once for 20 minutes. And this non-deterministic behavior is what makes quantum optimization pretty interesting, because it opens new ways to think about optimization workflows. You can get more solutions. Can you derive any insights about your problem by using this many number of feasible solutions for your problem? So we have talked about the problem, the complexity, our approach, and how quantum and classical solvers performed. And let's take a step back and look at the broader impact and what we have learned through this journey. To wrap things up, here are some key takeaways from this delivery. So the first question we wanted to answer to the customer was, is it a useful technology? And our answer was yes. If your problem is the right fit, quantum optimization can be a very powerful tool, especially when paired with a classical method. And the second question was when to use it. So if your problem has a large feasible region and time to solution is critical, then quantum can really make a big impact. And the third question was how to model it, because we tried different formulations, as I mentioned. So our answer was modeling choice matter a lot. I mean, in this engagement, trying with three different formulations, we experienced how big the difference could be if you model it right. So we didn't stop at our earlier attempt after trying the CQM solver. We kept using different approaches. And compact, clean formulation in this project made a big difference, and we got a much better performance. And the fourth question is how to run it. So unlike classical solvers, which we are used to run for longer, you just let it run, maybe for a week. Quantum tends to benefit from running with short but more frequent calls. So what's the ideal problem? Because they have lots of business problems, not only this one. Across their organization, they have lots of optimization problems, and we have been doing optimization with this customer for a long time. So the way we define is this. So one that uses binary and or categorical variables, has a wide feasible region, so it's trivial to generate a solution. And third of all, if you need fast results. So, and these kind of problems show up a lot in three places: in assignment problems, in scheduling optimization problems, and in routing optimization problems. And we think this use case was a great example of that. That brings us to the end of the talk, and thank you so much for joining us today. My colleague, Justin Lucas, who is the program manager for this effort, and I will be at the conference, so if you have any questions, ideas, or want to chat more about quantum optimization, or maybe fantasy football, please come and find us. You can also scan the QR code to connect with us directly, and we would like to continue this conversation, and thanks again, and we are looking forward to what we can all build together in this space.